So I'm Dominik Moritz from the University of Washington, where I work on data visualization for big data. Last summer, I was at Microsoft Research and worked with Danyel, Bolin, and SIGCHI on the challenges with exploring large data sets interactively. To illustrate this problem, let's say you're a market strategist at an airplane manufacturer like Boeing, and you want to target the market with a new model. Your manager wants to know whether they should design a long-distance or a short-distance plane. Let's do an analysis and see what planes are actually needed. To do that, we first download data about all commercial flights in the United States from the last 3 decades. The Bureau for Transportation Statistics provides this data. This takes a while because this data set is around 70 gigabytes. We then import this data into a database so that we can run analysis on it. Since the data is very large, this usually takes some time, but it only has to be done once. So now, to learn the distribution of flight distances, we can compute a histogram. However, since the data set is very large, this will take a while, so let's put this in the background and continue with the rest of the talk while this is happening. So when an analyst makes a hypothesis and creates a query to check it, or in general learns something about the data, which is what we just did, they send it over to the computer. The database or query engine then computes an answer to this query and returns it back to the user. They can then make sense of this result. With the feedback, analysts update the knowledge about the data, and they can use it to inform the next step of the exploration. And because there is a constant back and forth between the computer and the machine, the speed of exploration is limited by the round-trip time between thinking and executing. And exactly this round-trip speed is affected when the data grows. More data leads to longer processing times and delays until the computer actually returns the results to the analyst. And consequently, she has to wait, and maybe that's the time to get coffee, or in the worst case, get distracted by other activities. And having to wait and interrupting the workflow means that the analysts may lose their train of thought. Talking about trains, or better, airplanes, looks like the results have to return for our query. So this is the distribution of flight distances. The majority of flights are shorter than 1,000 miles. Maybe if we want to better target a certain area or a certain airline, we might ask a question like, what if we look at flights for Hawaiian Airlines? Well, again, we ask the query and send it to the database, but it takes some time because this data set is very large. The state of the art in big data exploration is really trying to address this problem of long query times. Solutions to this problem can be categorized in 3 groups. One approach is to distribute the query among multiple computers and recombine the results from different computers. While this works very well for some queries, it is very expensive to buy or rent many machines. And latencies are usually way beyond interactive speeds. Indexes or data cubes pre-compute and store partially aggregated results. At query time, the system can then assemble these partial results very, very quickly. Unfortunately, this requires expensive pre-computation and only works for a limited class of queries. The last approach assumes that the precise answer is actually not that important. We can take a sample, which is a representative subset of the data, and do our analysis based on the smaller subset. The idea is implemented in Approximate query processing systems, or AQP for short. Recently, these systems have gained popularity or regained popularity in the database community. They use samples to estimate the true value of an aggregation. To illustrate this approach, let's look at a simple example. To estimate the sum of a data set with only 25% of the data, so a quarter of the data, we can multiply the sum of the subset by 4. But because the system only has seen a subset of the data, we cannot be certain about the overall aggregate. So there's some uncertainty attached to the value. This also means that together with the query, the analyst or the person who writes a query has to tell the system about the amount of error that they're willing to accept, or how long they are willing to wait. However, if the error threshold is chosen too low, then queries might take a long time, and before enough samples have been scanned. Progressive visualization uses online aggregation to address this problem by showing analysts an aggregate as soon as a few samples have been scanned. As a system scans more data, the aggregation results can improve. While this allows more time to compute a result without making the user wait, it doesn't address the fundamental problem that the user has to decide when uncertainty is low enough. And you really have to watch the updates until this time comes. Oh, looks like the query has finished. So now we can see what the distribution of flights for Hawaiian Airlines. Oops, apparently we cannot. Well, there was apparently a problem with the query. If we had looked at the Wikipedia article, we would have noticed that the airline code for Hawaiian Airlines is HA, not HI. So the problem was simply an error in the query, which we can easily correct. Sampling would have been great here, right? We would have gotten the results back immediately, and we actually don't care about the attached uncertainty in this case. Okay, let's run this query, and it again takes some time, so let's continue to talk about approximate query processing. Approximate query processing is a very promising approach, but it has some problems that might hinder its adoption. First, the results are by their nature approximate and imprecise. To help the analysts judge whether they are willing to accept this approximation, systems need to clearly communicate the uncertainty. However, even doing that, the error guarantees that the systems provide are still only probabilistic. So if I'm sure, 95% sure that the value falls within some bounds, there's still some chance that they fall outside. And the question is, will your manager at Boeing be okay with this mistake? Or even worse, here, are they willing to accept that? Or even worse, errors can be arbitrarily large. They can be completely outside of those bounds, and there's no perfect guarantee that they will be within some bounds. Moreover, there are common aggregation functions which cannot be approximated, provably not approximated. A very simple one being the max. Joins are also very hard to approximate. And there are more problems that we discuss in the paper. In our project, rather than trying to find new algorithms or trying to solve unsolvable problems, we developed optimistic visualization, which is a user experience approach rather than systems or database approach to the challenges that are coming from working with samples in approximate query processing. Optimistic visualization builds on the assumption that approximation is mostly right, but it offers a way to detect and recover from mistakes in the approximation. To this end, the system that implements this idea lets analysts use approximate estimates, and the system then runs the precise query in the background. And the analysts can then use this to confirm their observation that they made earlier on the approximation. It kind of provides a safety net when the uncertainty is low, but the errors in the approximation are very high. And we designed this to give analysts confidence to use approximation. And hence also the title of our paper, Trust but Verify. Trust the approximation, but verify it with precise results later. And we implemented this idea in Pangloss, which implements optimistic visualization. In the query specification pane on the left here, analysts can specify a visualization by dragging and dropping fields or writing filters. These visualizations then appear in the center. While the analyst works on approximations, the interface visualizes the value together with the uncertainty. Currently, Pangloss supports two kinds of visualizations: bar charts and table heat maps for 1D and 2D, 1 and 2 dimensions. For bar charts, we use error bars, while for heat maps, we show a separate visualization of the approximation and the uncertainty. Approximate queries in the system run in Sample and Seek, which is an approximate query engine from Microsoft Research. When an analyst makes an important observation, they can remember the view and instruct the system to compute the precise result in a much slower SQL Server database. These background queries are then shown in the site so that users can see when the results are complete. Okay, let's look at this system in action on the flight dataset. Here you can see Pangloss working on a flight dataset which has about 170 million flights in it. The video is in real time. I'm only stopping it so that I can explain what's happening, but I didn't speed anything up. Every approximate query here returns in about 100 milliseconds over this 70 gigabyte data set. And this is on a single computer. When you make an important observation, for example, here you see that there are 3 decades of flights in this data set, you can write it down, which helps you then clarify later what observation you make, or and recognize whether there was a difference in what you saw and what you should have seen. By remembering, we make Pangloss run the precise query in the background. And since optimistic visualization places the updates in the background, we can continue on our analysis without watching for updates. For example, we can answer the question about the distribution of flight distances for Hawaiian Airlines. Note that every interaction here requires a new query. Adding a field, sorting, filtering, zooming, all of these submit new queries to this very, very fast database engine. Okay, looks like the approximate result shows us that the distribution of flight distances for Hawaiian Airlines is bimodal. There are a lot of short flights, some medium flights, and very, very short long flights, so let's ignore those for now. This kind of makes sense for Hawaiian Airlines, as there are long flights between the mainland and the island, and the short flights are all within the island. A few minutes after starting to run the precise queries in the background, the color scheme in the sidebar will change from orange to blue. And this indicates that the results are final. We can then open a precise view, and Pangloss shows us the true data instead of the visualization of the approximation and the uncertainty. For example, here, the approximation actually completely missed one flight in the 30 years. And this one was a flight that Hawaiian Airlines took from Pennsylvania to Hawaii, and there was only a single flight. And this was missed in the approximation. However, the precise query showed us this one flight. Optimistic visualization here was crucial to give analysts confidence in using approximation. To evaluate our approach, we conducted a lab study and a case study. It was important to us to be as realistic as possible in the case study. So in the lab study, we invited 5 participants to come into our lab, and they used the system that you just saw on the flight data set. In the case study, we invited 3 teams. One was the product insight team, another one was the social media team, and lastly, Bing. And they came, brought their own data, we loaded it into the system, and then they explored their own data with our system. The detailed findings are in the paper, but the most important takeaways from this were that approximate query processing works. It is a really valuable thing to be able to get quick answers. One of the participants said, seeing something right away at first glimpse is really great. For them, it really felt like using, accessing the full data. We also found that optimistic visualization worked really well. One participant said, I was thinking what to do next, and I saw that it had loaded, so I went back and checked it. The passive update is very nice for not interrupting your workflow. So compared to having to wait for a full result, the approximation was able to give immediate results, but users could later confirm it, and they weren't interrupted in their exploration. Lastly, our users also expressed this need for guarantees. One of them said, with a competitor, I was willing to wait 70 to 80 seconds. It wasn't ideally interactive, but it meant I was looking at all the data. And this was really important for them to be able to look at all the data, not just a sample, not just an approximation. We also found some limitations with the system, mainly around what features it supports. One of the participants said, when I'm using a system, there's a path that I need to follow. They were wishing to support, to be able to use other aggregation functions and other visualizations. We also found that users still struggle to understand the concept of working with approximate data. If you're only working with samples, some common assumptions do not hold anymore. One of the participants said, now that I've been sitting here for an hour, after I go back, it makes a lot of sense to have these annotations. But as I was doing it, I was thinking, I want to move on, I want to move on. Users weren't aware that they were using approximations. And we have to do a better job at communicating what it means to work with samples. To wrap up, Existing approaches to handling approximate results, like algorithms that provide tighter bounds or visualizing uncertainty, as well as progressive visualization, they don't solve the fundamental issue with uncertainty because they fail to recognize the user's need for certainty. Optimistic visualization addresses the problem of missing trust by providing a way to detect and recover from errors in the approximation. And this gives analysts the confidence to use approximate results. We think that optimistic visualization can help with the adoption of approximate query processing systems. In our paper, we did an initial exploration and found that the approach is promising. More research is necessary to figure out exactly when to notify analysts about updated results and how to encourage them to remember a view when they make critical observations. We're also very excited to see how systems can integrate optimistic and progressive visualizations. Before I end this talk, I want to make one more point, that this project was only possible because of a very strong collaboration between database and visualization researchers. This is the team that worked on this paper. And Bolin and SIGCHI are both in the database group. They have never published at SIGCHI. Danyel works in the HCI group, and I'm working on visualization at the University of Washington. Because we found it, we've not just learned things about the user experience, but also about what kind of things databases and approximate query processing engines have to support to better suit the needs for data exploration. We've also wrote a paper for the Human in the Loop workshop, which will be next week in Chicago. And there we'll be talking about the user experiences as well as the implications for systems that we've learned in this project. And with that, looks like the query that we asked earlier finally finished. Well, since we already answered the question with Pangloss instead of looking at the answer, I'm happy to take your questions. And if you want to try out what optimistic visualization really feels like, you can come to the Microsoft booth at 10:50 tomorrow and try our system. And with that, I'm ready to take your questions.
Please slide up in the middle. Thank you.
Hi. Hi, my name is Andy Echenike. I'm working with Informatica. I really like a lot of the stuff that you're doing, especially when it comes to sampling and whatnot. Did you come up with users feeling that the sample they were it was, and especially did any of your users report thinking that they were maybe working on the full data set, or if any issues they might come if they were eventually to transfer up for the full data set?
That's an interesting question. That's also why we wanted to run this case study, to really see how people work with a system like this. One thing we've learned is that although we try to really show very prominently that there is uncertainty in the data, that they are approximations. So we have error bars for the bar charts, we have the visualization of the uncertainty for the heat maps. For users, when they started to work with the system, they really embraced this being able to quickly iterate. And as I said, some of them kind of forgot that they were working with approximate data here. So we sometimes actually had to nudge them to explicitly write down their observations so that they use this optimistic visualization feature. Because, yeah, it's a very new concept to data analysts, but it looks very promising.
Perfect. Thanks.
Hi, Jae-Min Jo from Seoul National University. Great talk. I'm just curious, can the system calculate more difficult aggregate functions such as average or min or max? Or is the system only available for counting the number of rows in a specific bin?
Yeah. So the system that we're using is the sample and seek system. It supports sum and aggregate and some other aggregation functions. In general, you can do approximation for a large class of aggregation functions, including like quantiles. It is impossible to do it for max, to provide an approximation, or especially providing an uncertainty of the approximation.
Because it's very sensitive to outliers?
No, you just don't know what the max is. So you cannot say, okay, the max will be, is probably this value, but will be within these bounds. That's impossible. But for a lot of other aggregation functions like sum, you can do it. For aggregate average, you can do it. For quantiles, you can do it.
Yeah, thank you.
All right, it was a great talk.
Thanks.
Let's take our